Welcome to The Explainer. Today, we're going to pull back the curtain on the invisible force that powers pretty much everything you use, from the phone in your hand to the lights in your room. Let's dive in. Think about it. You flip a switch, you plug in your laptop, you start your car, you use it constantly. But have you ever really stopped to ask yourself, what is actually going on inside all those wires? That's the big question we're tackling today.
All right, to really get a grip on electricity, we have to start small. No, I mean really small, like atomically small. First, we need to clear up a common mistake and introduce the tiny particle that's the absolute star of the show.
You know, most of us think of electricity as just energy, some kind of magic juice flowing through the walls. But that's not the whole story. It's actually about the physical movement of a specific thing, an electric charge. And the particle responsible for almost all of it is one you've definitely heard of, the electron.
So deep inside every single atom, you've got these particles with charge. Protons are positive and electrons are negative. But here's the crucial difference. The protons are locked deep in the center of the atom. They aren't going anywhere. The electrons, though, they're buzzing around on the outside. And in certain materials, they're free to just jump ship. And that freedom to move, well, that's everything.
And all of this movement is governed by one super simple rule. That's it. Opposites attract, and things that are the same, they push each other away. This is the fundamental law of the land when it comes to electricity.
And you've totally seen this rule in action with static electricity. When you rub a balloon on your hair, you're literally scraping electrons off your hair and piling them onto the balloon. That creates an imbalance. And that little zap you feel when you touch a metal doorknob, that's just a tiny lightning bolt of electrons rushing across the gap to get things back to normal.
Okay, so that's static electricity, charge that's just sitting still. But to actually power your TV or charge your phone, we need that charge to flow. So let's look at the forces that give these electrons the big push they need to get moving.
This is probably the best way to think about it. Imagine water flowing through a pipe. Voltage is like the water pressure. It's the push. The higher the voltage, the harder that push. Current, on the other hand, is how much water is actually flowing through the pipe per second. You need both the push and the flow to get anything done.
But here's the thing, it's not a perfectly smooth ride for those electrons. As they're racing through a wire, they're constantly bumping and crashing into the atoms of the wire itself. It's kind of like trying to run through a really crowded hallway. This electrical friction, we call that resistance. And this brings us to something I am absolutely sure you've noticed. You've had your laptop plugged in for a couple of hours, you go to pick up the power brick and it's pretty warm, right? What's going on there? Yep, the answer is resistance. Every single one of those tiny collisions we just talked about. Every time an electron smacks into an atom, it converts a little bit of electrical energy into heat. Now add up trillions upon trillions of those collisions every second, and suddenly your charger starts to feel warm. It's just an unavoidable side effect of putting electricity to work. Okay, so we know how to get electrons moving. Now, how do we actually control this flow to make it do useful things for us safely? Well, it's all about creating the right kinds of paths for the electrons to follow.
It turns out electrons are kind of picky about what they'll travel through. Some materials, like copper and other metals, are like wide open superhighways where electrons could just zoom along. We call those conductors. Other materials, though, like the rubber or plastic coating on a wire, are like a total dead end, a brick wall. We call those insulators.
And here's maybe the most important rule of all. For electricity to work continuously, it needs a complete, unbroken loop to travel through. This is called a circuit. When you flip a light switch, you're not doing anything magical. You're just closing a tiny gap in the wire, completing the loop, and letting the electrons flow. That's it.
And that is why those plastic insulators are so incredibly important. If that plastic covering gets damaged and the two wires inside touch, the electricity takes a shortcut it's not supposed to. That's a short circuit. The resistance on this new path is super low, so a massive amount of current suddenly flows, which generates intense heat and can easily start a fire.
So where does this push, this voltage, actually come from? Well, it's interesting because the power you get from a battery and the power you get from a wall outlet are two totally different animals.
The power in your phone's battery is called direct current, or DC. Think of it like a river. The electrons flow steadily in one direction. But the electricity in your wall is called alternating current, or AC. In this case, the push on the electrons rapidly switches direction, back and forth 60 times a second. It's less like a calm river and more like a frantic tug of war.
This makes perfect sense of why many plugs have three prongs. You've got the live wire bringing the current in, and the neutral wire taking it out to complete the circuit. But that third, roundish prong, that's the ground wire. Think of it as an emergency exit. If something goes wrong and electricity is leaking, the ground wire gives it a safe, easy path down into the earth instead of, through your body.
So when you hear about a device being a certain number of watts, what does that really mean? Well, power, which we measure in watts, is simply the combination of the push, the voltage, and the flow, the current. The more watts a device has, the more electrical work it's doing every single second.
And finally, we get to the real magic trick. This is the discovery that changed everything. It turns out that whenever you have moving electric charges, they create an invisible magnetic field around them. This incredible link between electricity and magnetism isn't just a neat party trick. It is the engine of our entire modern world. It's the principle that makes every single motor spin in everything from your fan to a blender to an electric car.
Okay, I know that was a lot to take in, but now you have the core concepts. So let's do a super quick recap, and then I'm going to give you a mission to help you see this invisible world for yourself.
This is your new mental model. At its heart, electricity is just electrons on the move. Voltage is the push, current is the flow, resistance is what gets in the way and makes things hot, and all of it has to happen in a complete, closed loop called a circuit. Simple as that.
Now go out and be an observer. Try these things. Rub a balloon on your hair and watch it stick to the wall. You're seeing charge imbalance in action. Next time you unplug your phone, carefully feel the charger. That warmth? You're feeling resistance. And every time you flip a switch, just take a second to realize that you are the master of a circuit.
Look, understanding these fundamentals isn't just trivia. It's the key to understanding the technology that literally defines our modern age. This invisible force has built our entire civilization. Now that you get the basics of how it works, it really makes you wonder, what comes next?